In the last video that we studied, we looked at the definition of the convergence of a sequence. Now, it can be really tricky to actually use that in practice, and we don't really want to have to pull out that definition every time we've got a sequence that we want to show it converges. So what we're going to look at in this lecture is we're going to look at a couple of theorems that essentially give us a way of combining known limits together to get new ones, which means if we get some complicated looking expression, we can essentially just apply things like what we're going to do today in order to evaluate the limits rather than going directly to the definition every time, because that can be a bit tricky. So let's just state the first of these limit theorems, and it will look familiar for those of you who have studied calculus in the past as your limit laws, and it tells us how we can add, subtract, multiply, and divide. So here it is, the so-called algebraic limit theorem. So what we've got here is two limits. We've got two sequences a(n) and b(n), and we're given that the limit of these sequences is provided as limits a and b. And this theorem simply says that we can multiply, number one says we can multiply our sequence an by a scalar c. We better just note that c is a real number here. And that the limit will also be multiplied by c. The second part says if we take the limit of the sum of the two sequences, which means we take our two sequences and add them together term by term and look at the limit, then, as we would hope, the limit turns out to be the sum of the limits of the two sequences themselves, which is great. The third one says the same thing for multiplication. If both sequences converge, then the sequence that results from multiplying them together element-wise also converges to the product of those limits. And then finally, we've got one about quotients. We have to add one little technicality, which is that the limit of bn is not allowed to be 0. The terms bn themselves, I guess, could be. But if the limit itself is not 0, then the limit of the quotient of the sequences is a over b. So we'll just go through these one at a time and prove them. They kind of are proven in increasing order of difficulty. So we'll start with the first one, which is the limit of c times an is equal to c times a. Right, so our first theorem is that the limit of a scalar times our sequence just gives us the scalar times the sequence limit. Now, a good habit when we're starting to use the definition of convergence of a sequence to show something is to pretty much follow what will be the same template almost every single time. So remembering that our convergence definition said something like, for every epsilon greater than 0, there exists a capital N such that a whole lot of stuff. So a good way to start with a proof of this kind of thing is just to say, let epsilon be greater than 0. What that means is that following this, whatever is going to follow will depend on this epsilon, but it will be true no matter what epsilon we choose. So this is dealing with the for every epsilon greater than 0 parts. This is kind of an automatic first step for one of these convergence proofs. Then a good habit is to write down what we're looking for. It helps to remind us what the definition of convergence is and kind of sets us up for making sure we're hunting down the right thing. So what are we looking for? We seek n such that, now remember the statement is an minus a is less than epsilon whenever n is greater than or equal to n. This is what comes from the convergence definition. So we'll translate that into the terms of the problem we've been given. We've got our candidate limit, so the a for us will be c times a, and the an will be c times an. So we seek a capital N such that absolute value of an, so for us, our sequence term is c times an, minus the candidate limit value, which for us is c times a, is less than epsilon whenever n is greater than or equal to n. Okay, so for any convergence proof, this step is almost sleepwalking. It's almost completely automatic. We could teach a computer how to write this without too much difficulty. We'll always start with let epsilon be greater than 0. Then we can just write down what we're looking for, translate this part of it here into the language of the problem that we've got. So we're replacing the generic an with the actual sequence term we've got. We're replacing the a with the actual limit that we have in our problem, which is ca, and the epsilon is the one that we've chosen already. Now comes the tricky bit. Whenever we're doing one of these proofs, the hard bit is usually finding out what the n is. So a good habit is to just sort of mess around with the problem off to one side. This is not part of our actual proof. Just make yourself some rough working area And we're going to do some messing around with our inequality to try and figure out what our capital N should be. The actual formal proof part will probably just produce this N as if by magic, and then it will show that it satisfies the property we need. But actually the work in producing the N is what we have to do beforehand. Okay, so this one's not too bad. We'll start off by saying, alright, well, a good place to start is with our inequality, CAN minus CA, or even just with one half of it, and see if we can make it look a little bit neater. Okay, there's an obvious thing to do here, which is to pull out the C out the front. Don't forget you need to leave your absolute values on. So that can be equal to absolute value of C times absolute value of AN minus A. Now why do I want to do this? Well, finding AN minus A as a result of our manipulation is a really good thing. Why is that? Well, we know that AN is a sequence that actually converges. We already know that AN converges to A, which means we can make AN minus A as small as we like by choosing our n's to be large enough. And because we know already that it's a convergent sequence, we can make use in this proof to make this as small as we like. So we can say, for example, we can choose n such that absolute value of AN minus A is less than 0.1, for example, for all n greater than or equal to n. Now, 0.1 is not very convenient for our problem. It doesn't really mean anything. But what we could do instead is notice this is the thing that we've got control over. We've got control over AN minus A, and we're trying to make this thing less than epsilon. And we've also got that this thing at the top is related to AN minus A through this step here. So you usually have to do some work to relate the two things together, but we're making use of our A sequence converging to make AN minus A small, and we can make C times AN minus C times A small also by choosing a value that we like. We don't necessarily want 0.1 because that's completely irrelevant to our problem, but if we, for example, made it so that we choose our capital N such that AN minus A is less than epsilon, then that would mean that C times AN minus C times A would be less than C times epsilon, or absolute value of C times epsilon. That's closer to what we want. But actually we want it less than epsilon itself, so why don't we just instead make it that AN minus A is less than epsilon over absolute value of C. Now we're actually making a bit of an assumption that C is not 0 here. We'll dispense with that case in a second. But the important point here is we can make AN minus A as small as we like, including being less than epsilon over the absolute value of C. And if it happens to be less than epsilon over the absolute value of C, then if we go back up to here, the thing that we're actually trying to make small, this one here, is going to be automatically less than epsilon because we'll multiply by C and we'll get our epsilon that we want. So if we go back to our actual proof, we just say choose n such that absolute value of AN minus A is less than epsilon over absolute value of C for all n greater than or equal to n. Now the reason we can do this is because A is a convergent sequence itself, or AN is a convergent sequence itself, and so we are free to choose such an n. The convergence of the sequence AN guarantees for us that such an n exists, and we can just nominate it as the n that we want for our main problem. Then, the last part, so with part 1, state the problem, set up epsilon. Part 2, produce a candidate value of n. Part 3, demonstrate that this n satisfies the requirement that we need. So we want to show that the absolute value of C times AN minus C times A, if we choose this particular n, we want to show that this CAN minus CA is going to be less than epsilon. So we'll do the step of working we did over here before, which is equals absolute value of C times the absolute value of AN minus A. That is less than absolute value of C times epsilon over the absolute value of C, which equals epsilon. Okay, now we had that one little issue here, which was if c was 0, because c has been provided as just a real number. If c is 0, this whole argument doesn't work, but the situation reduces to be kind of trivial. So we'll just make a little extra in here. We'll just insert this, assume c is not equal to 0, and we'll just deal with the 0 case separately. So if c equals 0, the sequence is c times an just equals 0, 0, 0. And you can prove it that converges to 0 as an exercise if you like, or you can just take it on faith, which converges to 0. As required. Okay, so sometimes we get little corner cases that we can actually deal with quite straightforwardly by just setting them aside and doing them separately rather than trying to incorporate it into our main proof. Okay, that one wasn't too bad. For our next trick, we're going to do the second part, which is that the limit of the sum of the sequences is just equal to a plus b. Okay, we'll dive straight into our proof now. And we'll see if we can just follow the same sort of template that we followed for the first one. So we'll start off by just saying let epsilon be greater than 0. We seek n such that absolute value of an plus bn minus a plus b, which is minus a minus b, is less than epsilon whenever n is greater than or equal to n. So like I said, we can sleepwalk through this part. It's all automatic. It's just a habit that we can develop and practice using, and after we've done that for a while, we don't really need to think too hard about it. We can just write that down. So again, we're looking for a value of n, and we've substituted in the appropriate pieces into the expression involving epsilon. So again, we know that a and b both converge. So what we want to get is we want to get absolute value of an minus a and the absolute value of bn minus b involved somehow, because we know that because these sequences converge, we can make these terms, if we can produce them somehow, as small as we like by choosing appropriate values of n. So our aim is going to be to take our inequality, or at least the left-hand side of it, and try and turn it into something involving these two things here. So if I've got absolute value of an plus bn minus a minus b, again this one's going to pop out relatively straightforwardly. You can see that an minus a and bn minus b are both present in here. So that equals absolute value of an minus a plus bn minus b. I'm just rearranging the terms slightly. And I can now produce the two pieces that I want by using the triangle inequality. So it's going to be less than or equal to absolute value of an minus a plus absolute value of bn minus b. Okay, so we can make these two pieces here as small as we like, but how small should we make them? Because what we want is a less than epsilon. Oops. We want a less than epsilon over here, and we want to make these things appropriately small so that overall the whole thing is less than epsilon. How are we going to do that? Well, one little trick here that we've got to deal with is the fact that we want to deal with two different convergent sequences which will have two different values of n. So what I'm going to do is I'm going to choose an n1 so that this thing here is less than epsilon over 2. And I'm going to choose a different n so that this thing here is also less than epsilon over 2. This is for all little n's greater than those big n's. And if these two things are both less than epsilon over 2, then overall the whole thing is going to be less than epsilon. But the problem is we're going to choose n1 here such that this thing is less than epsilon over 2 for n greater than or equal to n1. And I'll choose an n2 here so that this term is less than epsilon over 2 for n greater than or equal to n2. So because a, n, and b, n both converge, we can choose these n1 and n2s to make the individual pieces satisfy the property. But remember, we're looking for a very specific single n so that the whole thing is true. But that turns out that's not too hard either. All we want to do is we just want to grab our n1 and our n2, look for whichever one is bigger, and take that. Because if n1 was 100 and n2 was 200, if I choose 200, then my n greater than 100 is also going to apply automatically. So my n is going to be the maximum of n1 and n2. Right, so now we need to go back. We've got kind of all the pieces together here. This is going to work. The last part is just translating it into our problem. So step 1, state the problem. Step 2, produce an n. Step 3, show that the n satisfies the properties. So we're up to the producing the n part. We need to set up what n1 and n2 are first. So choose n1 such that absolute value of an minus a is less than epsilon 2 for n greater than or equal to n1, and choose n2 such that bn minus b is less than epsilon over 2 for n greater than or equal to n2. Okay, so we're just having to make sure we say everything that we need to say so that the proof is going to be complete and not missing any pieces. So we've chosen an n1 and an n2 now. The last bit is to choose the actual n we want. Now we say let n be the maximum of these two pieces, n1 and n2. Cool. So now we've done step 2, which is to produce a capital N. The last part of the proof is to verify that this capital N has the properties that are required of it. So epsilon has been chosen arbitrarily. N has been specified. That depends on epsilon because these m1 and n2s depend on how big epsilon is. And so the last part is to show that our inequality is going to be true for the n that we've come up with. So now, if n is greater than or equal to this n, the thing that we want to deal with, an plus bn minus a minus b. Again, I'll start here, and I'll try and do some steps so that at the end of it, it becomes less than epsilon. So it's just going to an minus a plus bn minus b. You might argue this step is not strictly necessary, but it's quite nice in that it communicates to the reader of your proof what it is you're trying to achieve here. The grouping of the terms suggests that you're about to split it up, and so that in turn is less than or equal to absolute value of an minus a plus absolute value of bn minus b by the triangle inequality. And now, because of my clever choice of capital N, I know how small these two pieces are, so that is less than epsilon over 2 plus epsilon over 2, which equals epsilon, and that's what we're after. Just a quick note about my notation here. I've actually got a string of things. I've got a step here equals this, which in turn is less than or equal to this, which in turn is less than this, which equals this. Now, the way you should think of a set of statements like this is as if they were all lined up all along one big long line. Each of these signs just applies to the one before it. So this overall can be read as an plus bn minus a minus b is less than epsilon. Okay, it doesn't equal epsilon. The equals just applies to this part of it. The thing should be read as one big long expression. Okay, so that's part 3 done. We've shown that the n that we chose satisfies the properties that were required, and overall that means that our sequence converges correctly. Right, now we're really getting the hang of this. So the third one is the product one, and we know where to start now. We're going to start by just following the template, and we'll say let epsilon be greater than 0. We seek n such that absolute value of sequence term minus proposed limit is less than epsilon whenever little n is greater than or equal to big N. Okay, automatic statement, don't need to think about it, apart from to substitute the sequence we're dealing with in there. Right, this one's a wee bit trickier. Just like before, we know that we want to produce an an minus a and a bn minus b, because we can control how big these things are. So we want to take our expression here, sorry, an bn minus ab, and somehow extract absolute value of an minus a and absolute value of bn minus b here, because we can't do anything until we've got these, because these are the pieces that we can actually control the size of. So how do we do that? Well, we do the age-old mathematics trick of adding something and taking it away again to get the form that we want. So this thing here is equal to an bn. Now I want an minus a, right? So what I'm going to do is I'm going to go minus a bn, because that will factorize and give me the an minus a that I want. Because I've taken that new thing away, I better add it on again. And looks like that last piece will also give me a bn minus b. So we're on the right track here. The question is, how are we going to actually just make this work out? So again, we can use the triangle inequality in a second, but we'll just factorize out the pieces first. So that's going to be bn an minus a plus a times bn minus b. Cool. So far so good. We can make that less than or equal to absolute value of bn, absolute value of an minus a, plus absolute value of a, absolute value of bn minus b. Okay, triangle inequality implied. So we're making progress. We've got an minus a, bn minus b, they're both here. We can make them as small as we like. Just like we did with the first example, we can make this bn minus b less than overall less than epsilon over 2, and we can account for this a out the front of it. So this one here, we're going to do the same strategy as last time. We'll make this less than epsilon over 2, and we'll make this less than epsilon over 2. The right hand side, so we'll choose it. We want to choose an n1 and we want to choose an n2, just like we did before, and we just had to figure out how to make that work. So look at the second one, n2, using the same logic as we did in our first proof with the constant times a sequence. Then what would a good choice of n2 be? Well, n2 such that bn minus b is less than, let's have a think about it. What if we take epsilon over 2 times the absolute value of a? That will work, because when we go through and multiply this thing by absolute value of a, when we get to our actual proof, then the a's will cancel off and we'll get the epsilon over 2 we want. A is a constant real number, so that's all good. And again, we're going to assume a is non-zero to make it all work, but that's not going to be a problem. Okay, cool. So that's n2, but n1 is tricky because bn is not just a number. So I can't choose n1 such that an minus a is less than epsilon over 2. So what I'd want to do is like choose n1 so that an minus a is less than epsilon over 2 absolute bn. But I can't do that because bn is not allowed to appear in this expression here. Let's just try that again. Right near the edge of my screen. This is a no-no because this thing on the right is not a constant. Epsilon is fixed by this choice here, but bn is not a fixed number that I can choose. So that's not going to work. However, what I can do is I can actually choose a bound on bn itself that will make everything work. Because remember, bn is a convergent sequence, and we also know that convergent sequences are bounded. We showed that previously. So that means we can actually produce an upper bound on bn, and that will give us what we want. So we know that bn is less than or equal to m by boundedness. So that means that this thing, an minus a, is less than or equal to m an minus a. And now we just have the situation we had on this second piece over here. So we'll choose our n1 such that absolute value of an minus a is less than epsilon over 2m. Cool. That's going to make it all work. We've used one extra fact, which is that our convergent sequence B is bounded, to turn this Bn into a constant effectively. And then we go through the process and it should all come out. So the last step, or second step, sorry, is to produce the n. And again, we'll choose n to be the max of n1 and n2. It's just going to be a little bit more complicated to set up exactly what n1 and n2 are. So we're going to produce our proof now. The first part of it is to establish m so that we can choose n1. And then we'll establish n2, take the max of those, and that will be the n that we want. So this is what often happens with mathematical proofs, is it looks like we're pulling the facts that we need out of thin air. We're not. We've figured them out beforehand, and the structure of the proof suggests that we reveal these facts in a certain order. It doesn't necessarily reveal the way that you'd go about solving the problem if you didn't know the answer already. So when you're reading proofs, keep that in mind. The way the proof is presented to you is almost never the way that it was actually come up with. So you're not expected to necessarily understand immediately where all these things come from as you're reading it, but you do see how neatly they all fit together at the end. So first thing we need is our capital M. So we'll say choose M such that the absolute value of Bn is less than or equal to m, and we can do this as Bn is bounded. Okay, step one. That's good. So we've got this m. Now that we have m, we can choose our n1. Now we'll say choose again. Choose n1. So every time I'm saying choose, it's because some theorem has guaranteed that such a thing exists. So choose n1 such that the absolute value of an minus a is less than epsilon over 2m for all little n's greater than or equal to n1. Okay, so now we've chosen n1, took an extra step, which was to pick this capital M, but otherwise we're just proceeding exactly as we did for the previous one. Now we'll choose n2, such that absolute value of Bn minus b is less than epsilon over 2 times, what did we say it was? 2 times the absolute value of a for n greater than or equal to n2. And finally, we need to actually produce the n that we're after. So let n be the maximum of n1 and n2. Okay, so like I said, if you were reading this proof without having listened to this discussion beforehand, you would be thinking, where on earth have we plucked these random values from, and why are we doing this? But like I said, just remember, when you're reading a proof, that's not the logical thought that came up with the proof. It is the outcome of the working that came before. So, step 1 complete, state the problem. Step 2, produce ourselves a capital N. Tick, we've done that. So the whole point of what we just did was to define what our n was going to be. Epsilon is fixed at the start. We've chosen n. Our n will almost certainly depend on what our epsilon was, and it does indeed because of these epsilons in here. So everything is looking in pretty good shape. Now the last piece is just to present the working that shows that our sequence term minus the limit is less than epsilon. Okay, so let's go about doing this now. So saying now kind of sounds like we're about to do something important, so that's a good thing to write. Absolute value of a n b n minus ab Now, just because we did the working on rough paper over here doesn't mean we don't need to repeat it when we actually do a proper proof. Absolute value of an bn minus ab is equal to absolute value of an bn minus a bn plus a bn minus ab. Just repeating our working from over there, equals, this time I will lump the steps together, absolute value of, what is it, bn, sorry, times an minus a plus a times bn minus b, and suddenly this is all looking rather neat and tidy, which is less than or equal to absolute value of bn, absolute value of an minus a, plus absolute value of a, absolute value of bn minus b. Standard application of triangle inequality to split a sum up into two pieces. Now we can now say that's less than or equal to m an minus a plus, I'll just leave that one intact, absolute value of a times bn minus b. And now I can substitute in these two pieces here, which in turn is less than, these are strictly less thans because they are less thans, the way we've chosen the ends. an minus a is going to be replaced with epsilon over 2m, so m times epsilon over 2m plus absolute value of a times epsilon over 2 times absolute value of a, which equals epsilon as required. And the whole proof looks rather neat and tidy. We haven't really said anything we don't need to say. First part, state the problem. Second part, define whatever it is we need to define so that we can choose the end that we need to demonstrate. Third part, we've missed something off. We should say something somewhere about little n being bigger than our big N. So that only comes in when we started employing our bounds. So this is for only the step here, if n is greater than or equal to big N. So step 3 was to demonstrate that the n that we chose here satisfies the property that we require of it, which is that this inequality holds true. Okay, that was fun. One more to do. So for our final example, we're going to do the quotient one, and that is to say that the sequence of an over bn converges to a over b, provided our limit b is not equal to 0. Now we're not going to attack this one directly because this one looks quite close to the product one we just did. So what we're going to do is we're going to note that an over bn equals an times 1 over bn. So if we can show that 1 over bn converges to 1 over b, then we can use our product one. Okay, so as soon as we've got that 1 over bn goes to 1 over b, we can just use the third part, which is to show that products of sequences converge to products to give us what we're after. Then use part 3. So that's going to be our approach. Proof will show that 1 over bn converges to 1 over b, and then use part 3. Okay, it never hurts to state your intentions at the start of a proof. This is what we're intending to do. We're intending to show that this tends to 1 over b, and then we're going to use our previous part. Okay, so what we're really trying to prove here is this statement here, that the sequence 1 over bn converges to 1 over b. If we can do that, then we're done. Okay, so again, now that this is our new problem, we'll just state what we want to do, and then go ahead and do it. So same template as before, let epsilon be greater than 0. We seek n such that absolute value of 1 over bn minus 1 over b, substituting in for our sequence term, and our candidate limit is less than epsilon whenever little n is greater than or equal to big N. Okay, so, and we know that Bn converges, so we know that we want to get Bn minus b involved somehow, so that we can make that as small as we like, and then maybe something good will happen. Alright, so this one's a bit trickier. We've got a fraction difference here, 1 over Bn minus 1 over b, and we want to somehow rearrange this so that we get an absolute value of Bn minus b sitting on the top there. Okay, well, I can kind of see how that works. I can just combine these two fractions into one using our usual fraction tricks, and that will give me what will it be? Multiply by bbn, so it's going to be b minus bn over b bn. Yeah? Cool. That's got me what I want on top, and it's got a constant b on the bottom, but it's got an issue. Let's just write that in a slightly nicer form. This is the thing, I'm happy with this. I can deal with these. I'm also happy with having a number on the bottom. We had two other examples previously where that worked. But now I've got a bn term on the bottom of my fraction that I have to somehow deal with. Remember, for our product problem, we had a sequence term bn, well, it was an an, I suppose it was, on the top here, and we used the fact that our sequence was bounded to say that this thing here was smaller than some bigger number. Unfortunately, this time we've got our sequence term on the bottom of a fraction, which means if we were to show that this was bounded, then it's going to give us something greater than or equal to some other thing. And that's going to be completely useless, because we're looking for a less than or equal to inequality to deal with. So we had to figure out how we can produce a lower bound on b 1 over bn instead of an upper bound. 1 over bn to be greater than something positive. So how do we do that? Well, it turns out it's not too bad. It's just a case of getting used to it. So if 1 over bn is greater than something, it means that, 1 over bn to be less than something. That's what we want. That will mean that absolute value of bn is greater than 1 over that something, right? So we're looking for a lower bound on bn, not an upper bound. Right, so if we were to draw the number line for a second, let's put 0 on here, and I'm going to put the absolute value of our limit b just here. Now let's just think for a second, what happens as our sequence converges? Let's just say here are our sequence terms, and they're converging in, it's the absolute value of these, so I shouldn't draw them on the left-hand side like that. Let's try that again. Draw this back in. Our sequence terms are eventually going to mill around. This is the absolute value of bn. But because my sequence converges, eventually they're going to cluster in around this value b, right? So what that means is actually, we just need to find some number that's lower than absolute value of b, and eventually all of our sequence terms will be greater than this number. This is by virtue of the fact that bn converges. Okay, it has to be. So this is like the epsilon for the convergence of bn. We could make this value, nice sort of symmetrical looking choice would be absolute value of b over 2. And then this thing here would be the epsilon for bn that we can apply to get the n. Hopefully that makes sense. So remember that bn converges, which means that for any distance that I want, which I'm going to use b over 2 as my distance, I can choose an n so that if I go beyond that n, all of the terms are within that distance of our limit b. Works for absolute values too, so I'm going to make my distance epsilon for bn itself just absolute value of b over 2, that distance there. So that if I go beyond this, all of my terms are guaranteed to be greater than absolute value of b over 2. I don't actually care about what happens on this side. I'm just looking for a lower bound for my sequence, and absolute value of b over 2 looks like it will be a good one. Okay, so I'm going to choose an n1 such that absolute value of Bn minus B is less than absolute value of T over 2. Okay, so that's my epsilon distance, that's my sequence term, and that's going to imply, in particular, that absolute value of Bn is greater than the absolute value of T over 2, which in turn implies that 1 over absolute value of Bn is less than or equal to 2 over absolute value of T. And that's what we're going to need, because we were looking for an upper bound on 1 over Bn, and we've now got it, 2 over the absolute value of T. Okay, this is like the M we had before, but it's a slightly more complicated logic to get to it. Now I'm running out of scribble space, so everything from here kind of follows the standard way. So I'm going to choose N1 such that, we're being brave and writing our proof straight in before we've figured all the details out, such that the absolute value of Bn minus B is less than absolute value of T over 2. This implies, not T, what am I saying? I'm mixing my B's and my T's up. That's a B. Anywhere else I've done that? Here and here. And here. Then this implies that the absolute value of Bn is greater than the absolute value of B over 2, and hence that the 1 over the absolute value of Bn is less than 2 over the absolute value of B. Okay, so this part here is less than 2 over the absolute value of B. I now want to choose another n, so that this piece here altogether is going to be less than epsilon. We want epsilon overall, so to counteract some of that stuff, we're going to have epsilon times absolute value of B over 2, aren't we? Alright, now let's put that together. So we're going to choose N2, and again I've forgotten to say such that for n greater than or equal to N1, blah. Okay, now we'll choose N2 such that absolute value of B minus Bn is less than. Now we've got to make sure we get this all correct. There's an extra divided by B coming in here, so it's got to be is less than epsilon absolute value of B squared. That's to account for this extra one, all over 2 for n greater than or equal to N2. Alright, you may just have a little bit of a think about that one, check it actually makes sense to you. Now, let n be the maximum of N1 and N2. Okay, we've had to add two different n's here because N1 is the standard, N2 is the standard one that's going to get us the upper bound here that makes B minus Bn as small as we like. N1 was the other n we chose that that produced for us a lower bound on our sequence values, which gave us the upper bound for the reciprocal term that we have in our expression. Right, so got a bit complicated, but we've now done what we need to do. Step 1, state the problem. Remember, the problem we're solving is actually this one because the result follows straight ahead if we can get that one out. Step 2, choose a value of n, which has the maximum of my two n's. Step 3, show that the n satisfies what needs to be satisfied by the problem. So we're going to need to look at, remembering our lesson from last time, if n is greater than or equal to big N, absolute value of 1 over Bn minus 1 over B equals absolute value of B minus Bn over B times Bn, which equals absolute value of B minus Bn divided by absolute value of B times 1 over absolute value of Bn. Alright, now we can substitute in our various pieces. This is less than, first off, we'll do this one with his expression here. So that's going to be epsilon absolute value of B squared over 2 absolute value of B times, now also substitute in, let's get a different color, this piece using this piece here. So that's going to be a 2 over the absolute value of B, and lo and behold, a miracle occurs, everything cancels off, that equals epsilon as required. So now we need to make sure we actually link back to our original theorem, because remember we solved a slightly different problem and intended to use it to justify our original result. So hence 1 over Bn converges to 1 over B, and thus An over Bn equals An times 1 over B, and just to emphasize the fact that I've done them separately, converges to A 1 over B equals A over B by our product rule part 3. Okay, now I was going to do a second theorem, the order theorem, after this, but actually this video has got quite long already, so I think now is a good place to cut it off, so catch you next time.